All right. So, I need your full undivided attention, please. Yes. All right. So, today we are talking about what makes a reaction happen spontaneously. So, a reaction that just kind of happens on its own. And it has to do with entropy, which is a new concept, and free energy, which is a new concept. So those are our two new ideas today. So many chemical and physical processes release energy that can be used to bring about other changes. So we call this free energy. And you've actually already been dealing with free energy, like in our exothermic reactions, like combustion. So for this example, the combustion of gas releases free energy. And that free energy is what allows the pistons inside of a combustion engine to work. So reactions can occur spontaneously or they can be non-spontaneous. So a spontaneous reaction occurs naturally. So you don't have to do a lot of manipulation and favors the formation of products at your specific conditions. So at whatever temperature or pressure that you are working at, this type of reaction will occur naturally and it will create a lot of products. So sometimes you may need to initially add energy. So some energy may need to be supplied initially to get over that activation energy curve. So that's your EA. Spontaneous reactions produce substantial amounts of products at equilibrium, and they release that free energy. However, spontaneous does not necessarily mean fast. So a spontaneous reaction could be extremely slow, or it could be very fast, like burning. The speed of the reaction does not relate to spontaneity. So here are some examples of spontaneous reactions. So there's some exothermic ones and endothermic ones. These all can occur spontaneously. On the other hand, there are non-spontaneous reactions. Non-spontaneous reactions is a reaction that does not favor the formation of products. So it prefers to exist as it is in reactant form instead of products. And non-spontaneous reactions do not produce substantial amounts of products. So when we talk about favoring reactants or favoring products, non-spontaneous reactions favor reactants. All right, this is just a friendly reminder. We've been talking about this now for 2 units. Enthalpy is delta H. If you have a high delta H, a positive delta H, it's endothermic. And if you have a low delta H, it's exothermic. So we know that negative delta H is our exothermic. So just to be very clear, endothermic processes can be spontaneous. They absolutely can be. You see spontaneous endothermic reactions all the time. So for example, ice melting into liquid water is spontaneous. at room temperature, but it's endothermic. So if a spontaneous reaction needs a little bit of activation energy to get going, or a lot of activation energy, no matter what, it can pull the energy from its surroundings. So when ice melts, it's getting energy from the surrounding air to do the melting, even though it's endothermic. So reactions that require a lot of energy to happen but are still spontaneous, they have to do with something else, which is a new concept. So another factor that other than enthalpy changes that influences spontaneity is entropy. Okay, entropy is the fancy science way of saying chaos. So entropy is chaos / disorder. So entropy is a measure of the disorder of a system. So how chaotic is the system, how crazy are the particles moving, all of that would be a measure of disorder. And actually, the law of disorder in the universe is that the natural tendency is for systems to move in the direction of maximum disorder or randomness. So we as humans like things to be nice and orderly, whereas the universe says, let's be chaotic, let's have entropy. An increase in entropy favors a spontaneous chemical reaction. And a decrease in entropy favors the non-spontaneous reaction. So when you're ready, go ahead and flip your page. We're going to look at a few examples of increasing entropy. All right, so moving on to page 11, you have a chart on page 11 that looks at what increasing entropy looks like. So that should be the table's title. So if you could circle that. What does increasing entropy look like? So if we increase in entropy, we're increasing the chaos that's happening in the system. So if you look here, when you go from solid to liquid, you have very tight, nice, orderly particles, and then they start to spread out and relax a little bit. So that change from solid to liquid is going to increase particle movement. And increase randomness. So those particles will interact with each other randomly. And together, both of that means an increase in entropy. The same thing happens when you move from a liquid to gas. So when I go from liquid to gas, I get increased kinetic energy or particle movement, which means an increase in randomness. And both of those things lead to an increase in entropy. Additionally, In Unit 6, we dealt with a lot of entropy. Anytime you make a solution from a solid, you're breaking that solid apart and making that solid more chaotic. So here I have my solid solute, and as it goes into solution, I've separated that nice orderly solid into all of its ionic components, and so that is a higher entropy system. So when a solid dissolves, entropy increases. And that's what that picture underneath is showing you as well. I think it's even clearer how chaotic it is. So here you have your nice orderly solid in this very tight crystal structure. It goes into water and dissolves, and you can see the system is much more chaotic, so higher entropy. All right. Okay, so if enthalpy is delta H, entropy is delta S. So if you could just circle this for me. We're going to look at a chart that talks through what's going on with delta H and delta S. All right, the big columns or rows in this chart are the top row and the bottom row. When is a reaction always spontaneous and when is it non-spontaneous? If you have a negative delta H for your system, so we know that that means exothermic, right? So if you have an exothermic delta H and a positive delta S, which says right here, positive delta S means it's disorderly. So if your system is giving off energy and creating chaos, then it will always be spontaneous. That's really important. I'm going to jump to the bottom. If your system is endothermic, so it's absorbing energy, and if it is organized or orderly, then it's non-spontaneous. So under those conditions, the reaction won't happen. The other stuff's kind of in between. So by changing conditions, you can make something that is both negative delta H and negative delta S spontaneous. And by changing conditions, you can make something that's positive in both areas spontaneous. But if you see a negative delta H and a positive delta S, or a positive delta H and a negative delta S, that gives you very good information. All right? You can flip the page. Okay, so we are going to end notes today on Gibbs free energy, which is an equation that helps you figure out if a reaction will be spontaneous or non-spontaneous at specific conditions. So Gibbs free energy is the maximum the maximum amount of energy that can be coupled with another process to do work, which is a fancy way of saying how much energy is free and available. So if delta G, so in this equation, if it is negative, then this is a spontaneous reaction. If the system's delta G is positive, then it's non-spontaneous. So this is how you'll see the equation written on your quizzes and tests or on worksheets. Delta G is equal to delta H. So Gibbs free energy is equal to enthalpy minus temperature times entropy. So I rewrote it down here with parentheses to remind you that in the order of operations, you have to multiply your temperature and entropy first, and then subtract that from your enthalpy. Two other really important things in these equations. The first is right here. Your temperature has to be in Kelvin. So if you get a degrees Celsius temperature, you've got to convert it. The other thing is that your entropy units must be the same. So I'll show you in the first problem, 1 unit is in joules and 1 is in kilojoules. So I have to convert before I can actually do the math. If you make sure you're in Kelvin and then your entropy units are the same, then it's just plug and chug. So those are the two tricks to solving this. All right, so we're going to do one together. So here you have this reaction. It gives you delta H. It gives you delta S. And then it says calculate delta G at room temperature. And my room temperature is already in Kelvin, so that's great. So I'm just going to make my list of things, of variables on the left. So delta G is what I'm solving for. Delta H is given to me. It's negative 41.2 kilojoules. T is also given to me. That's 298K. And delta S is negative 135 joules per Kelvin. All right, so I see that I have an issue here because I have kilojoules here and only joules here, so I need to do a conversion. So negative 135 joules. How many joules are in a kilojoule? 1,000, yeah. So 1,000 joules in 1 kilojoule. So in my calculator or in your head, you can do the math here. Make sure you don't lose your negative though. So I get 0.135, and that's negative. So that's the number I have to plug in for delta S. So then I can just write my equation. Delta G is equal to delta H minus T delta S. And then plug in my numbers. So negative 41.2 kilojoules minus 298K times negative 0.135 kilojoules per. All your units will cancel in this situation. All right, so I'm going to do this first in my calculator. So 298 times negative 0.135. So I get delta G is equal to negative 41.2 kilojoules minus negative 40.23. And so then I can just plug that into my calculator. And remember, when you subtract a negative, you end up adding a positive. So you can either type it in or do it in your head. Yeah.
What do you
Which other formula?
the delta G for delta H minus T times?
It's the same one. I just put parentheses around it to differentiate or to show you where you need to put your order of operations. So the last question is the reaction spontaneous? So in this case, delta G was negative. So if I look back up at the top, I see that negative delta G is spontaneous. So that's spontaneous. So yes. All right, now you're gonna try the next one on your own. So take like a few minutes and try that. And then I'll put the answer up on the board in a minute. All right, when you're done, you can check your answer. So Gibbs free energy problems are essentially plug and chug problems where you're putting in all the information, but the two tricks, well really three. The three tricks are to make sure that your entropy and enthalpy units match, to make sure your temperature is in Kelvin, and then to really watch your negatives, because it's easy if you're doing it quickly or typing it into your calculator to miss a negative, and that will mess up everything. So here I have negative 502, so that's a delta G that's negative, which is spontaneous. All right.